Yeah, great. Thanks, Terry. Right. So now we've got four economists who are going to talk to us about this whole spectrum of modeling that Spiro introduced us to. The first one is Ron Sands, who also works for the Economic Research Service. Ron develops and applies global economic models, excuse me, for the integrated assessment of climate change. Spiro mentioned the farm model. I'm sure Ron will be telling us more about. Ron began his career at Pacific Northwest National Laboratory and then joined the Economic Research Service in 2009. He's also a very active member of the AgMIP Global Economics Modeling Group and has participated in many greenhouse gas mitigation studies organized by the Stanford Energy Modeling Forum, many of you I'm sure are familiar with. And Ron has his PhD from the University of Minnesota. Ron, just before you take over, just a quick comment to everyone. So we planned about an hour for this session, and I apologize, these are going to be a little bit kind of like speed talks. I asked each of the speakers to take about 10 minutes, so hopefully we can save a little time at the end for some further discussion, because I think there are a number of interesting questions we could talk about here as we after we hear these folks talk. So without further ado, Ron, go ahead and take over.
Okay, I'm going to try and share my screen now. Can you see my slides?
Yes, go ahead.
Okay, great. Thanks for the introduction, John. I've been a part of the AgMIP Global Economic Modeling Group for more than 10 years, and AgMIP has been good to me. The Global Economic Modeling Group has been quite successful in publishing some studies. And in my presentation today, what I'm going to do is give an overview of the sort of the global modeling landscape for AgMIP and for the Stanford Energy Modeling Forum. So these models are intended to simulate a number of global change drivers. And I like to group them into 6. One is population, one is per capita income growth over time, one is agricultural productivity growth, another is dietary preference. One we've really focused on is climate change impacts on agriculture, but also climate change mitigation is taking on an important role as well. So the key takeaway from this presentation will be that agricultural greenhouse gas mitigation within global economic models is highly stylized. A lot of details are left out, especially translating economic potential of mitigation activities to incentives for land managers and what would actually work on the ground. So some humility is needed on our part from the global modeling community, because one model can't do everything. Okay, now just move to the next slide. I'm going to give just a little bit of discussion about MIPS, model intercomparison projects. These have, in my view, become the gold standard for assessment of climate change science, impacts, and mitigation, which I guess also correspond to the 3 volumes of the IPCC assessment report that just came out. Prominent model and comparison projects are the Stanford Energy Modeling Forum. That's the original. Everything else is built upon that. That's been going on since the oil price shocks in the 1970s. Another very prominent one is the CMIP set of comparisons. The C actually stands for coupled. I've always thought of it as climate model in comparison, but it is actually called coupled, but it is composed of climate models. And also we have AgMIP, the Agricultural Model Intercomparison and Improvement Project. So features of all these MIPS are they're multi-model, they're scenario-based, multidisciplinary, and have a sustained effort over many years. And I think that's really important to remember that this is a sustained effort. So the diagram on the top right, this Venn diagram, shows or lists some of the global economic models that I've worked with those modeling teams. Within the green oval, we have the models in the AgMIP Global Economic Modeling Group. And in the blue oval, we have modeling teams that have been involved in some of the standard energy modeling for mitigation studies. And you can see that there is a fair amount of overlap there. As Spiro mentioned, I develop and maintain the Future Agricultural Resources Model. And I've been doing that since I started at ERS. So just a little bit more in the background of the farm model. All these models have a long time horizon, to at least 2050 and actually to 2100 for some of the studies that we're talking about. For the AgMIP Global Economic Modeling Group, we have 13 world regions, including the US as a single region. The farm model is dynamic recursive, meaning that it's essentially a sequence of static equilibria that gets solved every 5 years up to 2100, and the capital stocks are updated from time step to time step. So Spiro listed some of the indicators that come out of these models, and greenhouse gas emissions are one, also food consumption, crop production, et cetera, et cetera. I just thought I'd mention a few of the studies that I've been involved with AgMIP and the Energy Modeling Forum. One was in 2014, Jerry Nelson led the AgMIP Global Economic Modeling Group in the study of climate impacts on agriculture. The article was called Climate Change Effects on Agriculture, Economic Responses to Biophysical Shocks. The takeaway from that study, when you look at climate models being used to inform crop models, being used to inform economic models, the key takeaway is that the variability introduced by the crop models across different crop models was actually greater than the variability introduced by the various climate models that were used in that study. So that was quite interesting. In the Standard Energy Modeling Forum, we've done some studies of global biomass supply and demand to meet 1.5 C and 2 degree C targets. The study I'm currently involved with EMF is for the US. It's EMF 37, and it's a deep decarbonization study getting to net zero CO2 emissions for the US by 2050. So that's a bit of a stress test for the models that are participating. I guess that the key takeaway from this slide here is that a lot of learning takes place over time within MIPS through creative scenario design and a sustained effort. And in these modeling studies, we actually, start out with a set of scenarios, but they may get modified as we go through this and learn from each other over time. So if you're going to study mitigation in a global model, you need to have a target. And so there are two main types of targets that we simulate. One is a carbon dioxide only target. And as I mentioned, in EMF 37, we're looking at reducing CO2 emissions to net zero by 2050. And I guess the notion for that comes from the United Nations Framework Convention on Climate Change of stabilizing greenhouse gas concentrations at a level that would prevent dangerous anthropogenic interference in the climate system. So CO2 is a little bit different than the other greenhouse gases. In order to stabilize CO2 concentrations, you have to bring net CO2 emissions to zero. For the other greenhouse gases, their emissions matter, but we don't have the technologies to drive them to zero at the moment anyway, but they matter, and lower emissions imply lower concentrations and less of a climate impact. So the two main types of targets are a CO2 only target and an all greenhouse gas target, where the all greenhouse gas target is a more stringent target than CO2 only. So a good example of trying to meet an all greenhouse gas target, this is not from the farm model, this is from one of the other models that was mentioned on this slide here that I had earlier. This is from the GCAM model. This is the group I used to work with at Pacific Northwest National Laboratory. It's a global change analysis model. This is analysis done for the US long-term strategy, pathways to net zero greenhouse gas emissions by 2050. This looks at 6 strategies for reducing net greenhouse gas emissions to zero with all greenhouse gases. Energy efficiency is one of those. Decarbonizing electricity is one. I guess energy transitions, which could involve low carbon fuels, non-CO2 reductions. A lot of those are in agriculture. Land sink, which would be natural storage, carbon storage solutions, including afforestation, biochar, agroforestry, and then CO2 removal technologies, which could include what's called BECCS, bioenergy with CO2 capture and storage. This type of scenario is not easy to run. And, but there's a very important role for agriculture here, as I mentioned in some of these strategies. So for the non-CO2 reductions, the modelers rely on marginal abatement cost curves that come from the US Environmental Protection Agency. And in the top right is a picture of the cover of that document. The original version of this document, which was done, at least 15 years ago, I believe, was constructed for the Energy Modeling Forum study on non-CO2 greenhouse gas emissions. So these marginal abatement cost curves actually bundle up a fair number of different activities. And from agriculture, there would be activities like manure management, reducing enteric fermentation, reducing nitrous oxide emissions from agricultural soils, or methane emissions from rice production. The marginal abatement cost curves produced by EPA cover the world, including the US. And these are actually essential, I think, for probably all of the modeling teams in terms of modeling some of these agricultural options for greenhouse gas mitigation. But these are highly stylized. And yesterday in Sarah Orell's talk, she mentioned the difference between technical potential, economic potential, and going beyond that, more of a competitive potential. What would actually work on the ground? What are the competitive options that these mitigation strategies face? So the marginal abatement cost curves produced by EPA provide a very valuable service for the modeling groups in that they give us a notion of the economic potential of these mitigation activities for non-CO2 greenhouse gases. But going forward, there's a large gap between that and what's going on the ground and in specific geographical locations. So basically what I'm trying to do is say that a lot of detail is left out in the global economic models. In terms of implementation of mitigation strategies, we're really going to rely on information from regional models and from knowledge from others in other countries. So just to wrap up here, one of the real strengths of AgMIP, I think, is that it provides a lot of folks working on regional analysis, what's going on the ground in individual countries. And it also has a lot of developing country participation, certainly relative to the Energy Modeling Forum. Those are incredible strengths, and AgMIP activities will certainly inform what's going on the national modeling landscape. So I will stop there.
Great, Ron, thanks. That provides us a really nice big picture to understand how, like you said, we can then connect down to the national and subnational farm levels. And that's, I think, the theme of our next speaker, Roberto Valdivia, who's a senior researcher in the Department of Applied Economics at Oregon State University. He co-leads the regional economics team of AgMIP, and his research focuses, let's see, do we have Roberto here?
Yep.
Yeah, there he is. Okay, hi, Roberto. His research focuses on economic modeling of agricultural systems from farm to regional and national scales. And also Roberto has led a lot of the AgMIP work on participatory methods to develop future development pathways and foresight analysis. And he holds a PhD in development economics from Wageningen University. So Roberto, go ahead, take it away.
Thank you, John. Let me share my screen. All right. Can you see my screen?
Yes.
Okay, good. Yeah, thank you for the introduction, John, and good morning, everybody. And thank you for the invitation to be part of this panel. I will briefly talk about what AgMIP is doing to advance the methods for linking global, national, regional, and farm scale data and models. As Ron was saying in his presentation, like for example, global models are very stylized and don't have the details that are needed, that usually more farm or regional levels can include. So let me see if I can move my, all right. One of the key insights from the work that AgMIP and partners have been doing with the stakeholders in many countries is that there is an urgent need to design and implement national climate policies and agricultural development policies with local relevance. What does this mean? There is a need for understanding how these policies, national level policies or technology interventions may impact agricultural systems and farmers' livelihoods. Policies are usually designed and implemented at national level, right? While we know that adoption of technology interventions or adaptations take place at the farm level. And adoption of these interventions can be influenced by socioeconomic and biophysical conditions, or what we call socioeconomic and biophysical heterogeneity. Likewise, we can think about the response to shocks or changes like climate change can be influenced by heterogeneous conditions. And that's why we may have farms that win from climate change while others may lose from climate change. I just saw a question on the chat. Somebody was asking about whether climate-smart agriculture is profitable or not. I would say it depends, and in part, probably depends on these conditions, socioeconomic and biophysical heterogeneity. For some farmers, it may work, and for some farmers, it may not work, right? But we need to find what we can do to increase adoption of CSA technologies. But then ignoring this heterogeneity may also cause that broad policies or interventions could lead to increasing inequality or other unintended consequences. Therefore, analysis of key agricultural systems in a country are needed for development, testing, and implementation of CSA technologies at farm and subnational levels. So this is the kind of information that the stakeholders need to support policy decision-making, planning, and setting priorities for investment. The AgMIP Integrated National and Regional Assessment, or what we call INARA, tries to capture the complex nature of the agricultural sector across scales. INARA links data, models, and scenarios for consistent multidisciplinary, multi-scale, multimodal, and forward-looking assessments designed to help stakeholders assess risks and design mitigation and adaptation solutions. John Antle, on his presentation yesterday, mentioned the need to invest in data and computational science to design and evaluate CSA policies and technologies. Well, in fact, INARA is the kind of framework that uses computational science, multidisciplinary teams, data, and models to develop coordinated national and regional assessments. And the framework is that figure on the right-hand side of this slide. I'm not going to describe this in detail, but I would like to highlight some of the main components. The top part are all the global change drivers that include global socioeconomic scenarios, climate projections with different concentration pathways or RCPs, global crop models and global economic models, outputs like the ones that Ron just described on his presentation a little bit ago. And this feed into the national integrated assessment, which is the box just below the global data models, and to the regional integrated assessment, which is the box at the bottom of the slide. The national level component starts by evaluating the country's current policy conditions and strategic plans. For example, in many countries have developed what they call the Vision 2030, for example, which includes sets of policies and interventions to achieve sustainable development goals, They also include the planning or the processes to develop their national adaptation plans or NDCs to meet their commitments with the Paris Agreement for climate change. So based on these conditions, future agricultural development pathways are co-developed with stakeholders. We call them RAPs, Representative Agricultural Pathways. These pathways are plausible future socioeconomic and technological scenarios that capture the design and implementation of different national policies that may affect the agricultural sector. Then with that information, we can run crop, livestock, and economic models at national level to assess the impacts of each pathway and under different scenarios, including climate change. Then at the same time, at the regional level or subnational level, regional integrated assessments for key agricultural systems are conducted following the approach that was mentioned yesterday by John and Cynthia and described at the bottom of the slide on the left-hand side. The goal here is to conduct regional integrated assessments for key agricultural systems or key agroecological regions by integrating climate, crops, livestock, and economic models and data, and scenarios and adaptation strategies that are co-developed with the stakeholders. The crucial part of this framework is the component that you see in the middle, where we call the National Regional Data Interface. There needs to be a process to harmonize and make data across scales compatible. In other words, national models, for example, need to be able to get data from regional models. For example, adoption rates of specific interventions that are estimated at the subnational level. Likewise, regional models need to get data from national models, like price projections for different scenarios. One observation I would like to highlight is that at this point, it is very challenging to link these models and data across the scales automatically. So for now, what we are doing is identifying the key parameters that need to be shared across the scales and creating an input-output file, basically on a spreadsheet that contains information and the parameters that are needed to be transmitted across the different scales. But that's a place where, for example, investment in computational science would help. The other element that is important in this framework is how to translate the results into recommendations for decision-making, dissemination and communication of results. In AgMIP, we have a web-based tool called Impacts Explorer, where all the results publications are contained. And it's the box on the right-hand side of this diagram. It is basically a dashboard where users can explore the results for different countries, look at different scenarios and how climate change or policy interventions or new technologies can impact the farming systems in different parts of the world. Now, all of this seems fancy and easy, but it's actually challenging to implement. And one of the major challenges is data availability and data that is suitable to conduct these assessments. In particular, in developing countries where data is not available or difficult to obtain, right? So in these cases, we had to implement the regional integrated assessment using what we call the minimum data approach, relying on secondary data, expert opinion, and other data to at least have an approximation of the behavior of the production system. Here in the US, like in the application that John mentioned yesterday in the Pacific Northwest, the agricultural census data was used. And as Spiro mentioned earlier today, there is data from ERS and other data that might be available. But this is an important point that comes back from the need to invest in computational science, which includes also the need to collect data in a more efficient way and data that is appropriate to do these integrated assessments. So the investments on data like what ERS is doing, as Spiro mentioned today, are important and can create also opportunities for collaboration between ERS and AgMIP. And of course, accessing the data with a new system that Spiro just described will also contribute to advance the modeling work. So to finish, I'd like to show you the feedback from national level stakeholders in Ghana about the AgMIP approach I just described. This is part of the results from an 18-month project funded by IDRC, where we worked in Zimbabwe, Ghana, and Senegal to actually develop the protocols for INARA, and with direct engagement with the stakeholders during the duration of the project from the beginning to the end. And this is actually a follow-up project from a much longer project where we developed the regional integrated assessment protocols in these countries and many others in Africa and South Asia. So this figure, it's included in a policy brief that was co-developed with the stakeholders, where they highlight how AgMIP can contribute to improve policy decision-making in the processes in Ghana. And what they state is that AgMIP can provide evidence-based research methodology that generates results to support the national adaptation plan process that the country is doing, using current and forward-looking scenarios co-developed by scientists and stakeholders, and regional integrated assessment tools. And they also see AgMIP contributing to the provision of reliable quality data on climate projections, and also providing information of economic feasibility of potential climate change adaptation strategies. And by the way, we are adding mitigation to the framework, and we already have some results in terms of mitigation. And then conducting assessments at the regional, or what we mean regional subnational level, that capture how climate change policy or technological interventions may impact farming systems and farmers' livelihoods. These are the kind of information that are required to support decision-making at national level. And finally, they see AgMIP contributing to capacity building in the use of tools and methodologies required for forward-looking climate change adaptation analysis and planning processes. So I think this is my last slide, and I invite you to visit our website and the AgMIP Impacts Explorer, which is currently being updated and redesigned. That's all. Thank you.
All right, great. Thanks, Roberto. Really useful perspective on this challenge of linking models from the global, like Ron said, down to the farm level, so we have that on the ground detail to understand technology adoption and the issues Roberto raised about heterogeneity. The other two speakers we have on this panel, we invited to provide more, you might say, sort of granularity, I think, on this theme of, you know, the modeling challenges we face, particularly at that more granular farm level to regional scale, that is really important for understanding what we mean by CSA technologies and their potential to be adopted. The first speaker who will take that challenge on is Pierre Merrill from UC Davis. He's been on the faculty at UC Davis in the Department of Agricultural and Resource Economics since 2007. His current research focuses on food policies and climate change impacts on agriculture. He's also conducted research on industrial organization in the food sector, environmental and climate policy, and agricultural labor. Pierre comes to us from an engineering background at the École Polytechnique in Paris, and he received his PhD also in Ag and Resource Economics from UC Davis. So Pierre, hope you're with us. Yeah, looks like you are. So take it away.
Sorry, can you guys hear me properly?
Yes. Yeah, and we see your slides.
Yeah, thank you for the introduction, and thank you for inviting me to talk, even though I'm not part of the AgMIP network, but I have done some work in the past on climate mitigation from California agriculture. So I have a little bit of experience in the area, and I'm still very much interested in these topics and enjoying the conference so far. So what a lot of people have asked, what do we mean by climate smart agriculture? And you know, I've asked that question myself, and you know, as it stands, I see at least two two types of meaning that we could attribute to that moniker. The first one is lessening climate impacts, what we can call also adaptation to climate change. And the second one, which I think is perhaps the more relevant one and the one that has been more emphasized in the previous talks, is mitigating agriculture's contributions to emissions. So that what we call proper mitigation. And economic theory has very different things to say about these two aspects. That's why I'm kind of like trying to separate them, because the economic and the policy implications are going to be different, whether we talk about adaptation or mitigation. So with respect to adaptation, economic theory suggests a quite limited role for policy because of private appropriation of costs and benefits. So this is your typical invisible hand of Adam Smith. If markets are free to function and do their wonders, then individual agents, farmers, in this case, are going to adopt the right amount of adaptation. And so you would have to make a case for why policies or governments would need to intervene. And I'm not saying that necessarily the case cannot be made, but it has to be made for economists to agree that there is a desirable policy to be implemented. And one prime example of this is coordination issues, in particular with respect to agricultural R&D, which is not new. It's not a new topic. Particularly basic research, fundamental research that is not easily appropriated by economic agents. There is a case here for government support. However, even in terms of research, we can design institutions that provide incentives for agents to engage in research. In our case, research that is going to be designed to atone for the negative effects of global warming. And I would like to draw, your attention to recent work by Jacob Moscona called "Flowers of Invention," which is a great study about how intellectual property rights can act as a yardstick of agricultural innovation, using historical data on patenting for agricultural crops. So that will be it for adaptation, and the rest of my talk will be focusing on mitigation. And indeed, I think that's what most of the previous speakers have mentioned so far. So with respect to mitigation, there is a much more evident role of policy, and perhaps also as a result of that, of economic science, because greenhouse gas emissions are a prototype of a production externality. And we know as economists that markets are not very good at allocating goods and resources in an economy with externalities. Here, the idea is that farmers bear the cost of mitigation, but everyone else, including someone at the other end of the planet, benefits from lower emissions. So there's an incentive problem which may be mitigated or partially resolved through policies. Now, saying that there's an externality is one thing, saying that policy is desirable is another. There may be cost to policy that outweigh the benefits. So in some cases, the best thing is to do nothing. And indeed, even in jurisdictions with ambitious goals of mitigating greenhouse gases, agriculture, for the most part, has been left outside of these efforts. I see renewed interest, and I'm happy to see that. But the issues remain, and they've been highlighted yesterday by Undersecretary Bonney to some extent. The first of these issues, which is tremendous, is that of measurement of greenhouse gases. It's much easier to regulate point sources where you have end-of-pipe measurements of emissions than agricultural fields or animals. And so that means that, at least in the likely future, if we design incentives to reduce agricultural greenhouse gases, we're going to have to rely on verification, monitoring of practices. which implies we need to know, to infer how many greenhouse gas emissions are saved by the adoption of these practices, which raises even more issues, right, of scientific accuracy, of perhaps legality as well, of equity, political acceptability, and scalability. Just because we have incentive programs in place doesn't necessarily mean that they're going to be adopted to a large extent. And so before we invest in perhaps costly administrative structures to implement these schemes, we need to be confident that they're going to be adopted to an extent that makes a difference, right? Because there are other ways to abate emissions from other sectors. So there's competition, if you want, between reducing greenhouse gases from agriculture and further reducing greenhouse gases from other sectors of the economy. So this need for potential need for policy advice means that there's a public demand for bioeconomic models that can help inform policymakers about the effectiveness, the relative effectiveness of different policy options to incentivize greenhouse gas reductions. And here, we have a prime example of a demand that is put on the scientific community to come together across disciplines, because agronomists by themselves or climate scientists by themselves, cannot really compare these policy incentives, and then economists need biophysical information to populate their models. And it's one thing to model behavior and to model how markets may transmit price signals. It's another thing to know how a given practice in a given context is going to contribute to emission reductions. And so designing incentive schemes and predicting adoption often requires making assumptions, not only on the natural science side, which I'm not really qualified to talk about because I'm more of a user of these biophysical process models, but also on the economic side. And these assumptions often pertain to how farmers and ranchers make management decisions. So typical assumptions would be, cost minimization, profit maximization. If you want to take into account risk management, you may have models that specify expected utility maximization, but there is always some purpose. And then there are also sometimes strong assumptions about how markets work. And default assumption is perfect competition, right? This is important, especially when studying the potential impacts of local policies on leakage, because the way that leakage works is through price signals. So for example, if the US adopts an ambitious mitigation policy that reduces productivity in the US, then crop prices are likely to increase, which will induce land use change elsewhere on the planet. And as Undersecretary Bonnie highlighted yesterday, we may want to be aware of that before we put these policies in place. So here's an example of what these types of integrated interdisciplinary models can yield, and this is from my own work with Chloe Garnache, looking at mitigation from agricultural cropping systems in the California Central Valley. These graphs may be reminiscent of some of the graphs that were presented yesterday by Sarah Orrell from the EPA. Indeed, there are marginal abatement cost curves. I think that the horizontal axis or its scale might be much different from what she presented, because this is, again, only for California, only for crops, and it's even a subset of crops, because here we're using DayCent, it's the biophysical process models. And DayCent is not calibrated for all of the specialty crops in California. So we're only looking at a subset of crops, but what you can see is that, about 1 million metric tons of CO2 equivalent per year may be abated by this subsystem at a marginal cost of $20 per ton. And that's the blue lines are basically showing you the economic potential schedule on both panels. And then the other lines in orange and yellow and purple are going to be supply curves that would arise in the more likely case where we cannot implement that full economic potential because precisely of monitoring, measurement, and verification issues. So in that paper, what we did is first derive the first best, so the blue line that shows you the economic potential, how much it costs at the margin to supply an additional unit of abatement from that system, but then also investigate feasible policies. So policies that would be more likely to be implemented because of either data requirements or political acceptability and things like that. So on the left panel, what we looked at is what if you don't know at a geographically disaggregated level the full extent of the emission process, but you have sort of geographically aggregated knowledge of this emissions process. And so what you get, obviously, is a higher cost supply of abatement. So the curves are shifting to the upwards, if you want. So any amount of abatement is going to be supplied at higher marginal cost. And so you have two curves, one that delineates what would happen if we had one set of emission factors for the Sacramento Valley and another one for the San Joaquin Valley. And then the yellow one, what would happen if you had only one set of emission factors for the entire Central Valley. And what you see is you lose some, but not much of this abatement potential. Now, on the right-hand side panel, it's a much different story when we look at policy schemes that would be rewarding practice adoption in isolation or in combination. And the most striking is the purple line, which shows you the marginal abatement cost curve for nitrogen fertilizer reduction. So incentives to reduce fertilizer either through subsidies or nitrogen taxation. And here there is very hard to elicit much abatement at all, at least not relative to the first best. The second margin of adjustment that we looked at was tillage. So we had a tillage perturbation index that and the incentive was based on that index. And so here what you see is that it's performing better, obviously, than the nitrogen incentives, but it's still not giving you the full economic potential. And then if you combine the two, you get a little bit more of the abatement. So that's a type of policy outcomes that can be obtained from these integrated models, and that hopefully is useful when thinking about ways to incentivize greenhouse gas emissions in practice. The other thing I would like to talk about a little bit is the more on the modeling side, because that's kind of what I was asked to do. And I would like to talk about the trade-off between reduced form and structural modeling in economics. So this is more for the economic portion of these interdisciplinary models. I'm not certain that there is such a discussion right now in the natural science, but it's a very vivid debate, or it has been for many, many years. And basically, the idea is that there's a trade-off between empirical accuracy or empirical grounding, if you will, and the usefulness of economic models for policy designs, with the reduced form models being the ones that have a more solid empirical grounding. So they're typically estimated using lots of data, at least relative to the number of parameters that are being estimated. So that's a big advantage, and that's what the kind of proponents of this approach have been arguing. Now, the disadvantage is that these models typically reflect past adaptation, so they're not very good at predicting the future, and notably predicting new things, like we were talking about cover crops before, so that would be very difficult in that setting. They are mostly geared towards evaluating existing or past policies and not new policies that haven't been implemented in the past. So a good example of that by Locke et al. And one of my colleagues is also a co-author on that study, is a study that looks at the carbon intensity of corn ethanol under the RFS. So it's part of the model is reduced form. There is also a linkage with biophysical process models. But again, the possibility of counterfactuals is inherently limited in this type of exercise. In contrast, structural models, which is the approach that I have taken myself in the past, incorporate both physical and behavioral structural processes, and they're geared towards rich counterfactual welfare analysis. And another good example, very good example of that is a more high-scale model of the world trade in crops by Costino et al. That's also a paper I recommend looking at. It's not about mitigation, it's about adaptation, but the structure of the model is particularly elegant and transparent. And so that's why I'm citing it here. So the shortcomings of this structural approach is that it often involves a large number of parameters. This is not so true in the Costino paper because it's very stylized. It's not even so true in the paper I mentioned with Chloe Garnache because we're only looking at it's a regional model with a handful of crops, so it's not too parameter intensive. But there is a tendency of these models to have lots of parameters, and as a result, when presenting results, there is often a lack of transparency, or that's a criticism that is often made. And then another problem that is worth mentioning is that they're kind of prescriptive because they make a lot of assumptions, as I indicated, regarding behavior, regarding how markets work. And so as a result, they may overestimate adoption, because if a new practice looks good on paper, these models are going to have a tendency to say that they're going to be adopted. And we know that there are behavioral or psychological hurdles that may lessen adoption. And so I would tend to think that these models are going to be better at comparing policy outcomes than making sheer predictions about the extent of adoption. So my last slide is about avenues for improvement. So one thing I've tried to do in my own work is to better articulate biophysical relationships and economic functions. So there's a chronology to these models in the sense that the biophysical information comes first and is used as an input in the economic model. It's not the other way around, or I mean, there is some of the other way around going on, but not so much. And so I think there's a thing to be said about trying to incorporate that information in a way that is transparent, internally consistent, and that makes for a transparent communication of the model results. And that can be quite a bit of work, and it's not always done that way. Then my second point would be about strengthening the empirical basis for calibrating key behavioral parameters. And here I'm again referring maybe to the Costino paper, which is extremely elegant in that respect. Another point is that economic model architecture should be designed with welfare counterfactual in mind. I know that this is not always the only outcome that matters for policymakers or stakeholders. They may be interested in things like acreage, production, prices, in and of themselves, but structural modeling allows for welfare counterfactuals, and I think economists should keep that in mind where designing their model architecture. How are they going to get at welfare eventually? And then a word of caution, I guess, about this apparent abundance of data that we've been hearing and that we do have, notably through, I don't know, satellite imagery is an example. Typically, economic agents are going to make decisions about, about profits, right, from activities, from agricultural activities. Even if they are, risk averse, they're going to maximize the utility of profits. But at the end of the day, you need to subtract costs from revenue. And we have a lot of very detailed data on revenues and yields and acreages, but on the cost side, there is still a dearth of data. And I think we're far from having a level of disaggregation on the cost and input side that matches that on the output. And so this may limit what we can do. And I think researchers should be very transparent about this. Another thing that was highlighted also by Undersecretary Bonney yesterday is the linkages when looking at regional models, linkages through commodity markets and potential land use changes from local policies. If you're looking at big enough areas, then changes in output are likely to affect prices, which will then provide incentives for expanded production elsewhere. So it's one thing to say there's greenhouse gas mitigation potential in the US, but if the realization of that potential means that there's going to be even more emissions elsewhere, then this is a lose-lose situation that we don't want to get into. So I think modelers should be, worried about this. And then my last point is about equity aspects in integrated assessment models of the kind that I discussed. And I don't have a very, complete view of the literature, but my sense is that there is room for improvement there. I think it's going to be challenging to look at equity on the supply side unless you go into very detailed farm models. But even there, a lot of these models are long run and farm managers come and go, soils and climate don't. And so it's delicate to design these models with equity on the supply side, where I think there is perhaps more easier way to integrate equity aspects in this model would be to look at impacts on the consumption side. For example, impacts on food prices. This is something that I'm working on currently, not in terms of climate, but in terms of organic expansion, organic acreage expansion. And so to the extent that different categories of consumers purchase different foods and food prices are going to increase to different extent. If we implement these policies, these environmental policies, there might be distributional impacts that are worth documenting. And so I think that there's plenty of data on the consumption side that can be leveraged to make reliable statements about how environmental policy may affect consumers from different groups, be it income groups or racial groups or different types of segmentation of the population. So with this, I thank you for your attention, and I'm happy to answer questions. And this is a picture of the paper I mentioned with Chloe and co-authors.
Great, thanks, Pierre. I think in the interest of time, we're going to have to move on to our last speaker. But Pierre, I think, did provide a nice overview of some of the both conceptual and modeling issues that we face at the more disaggregate scale. And one of those that Pierre, you mentioned, of course, is the behavioral aspect. And our last speaker, Kent Messer, is going to be able to address that aspect well, I'm sure, because that's really the emphasis of his work. Kent is the S. Halleck DuPont Professor of Applied Economics and the Director of the Center for Experimental and Applied Economics at the University of Delaware. He also co-directs the Center for Behavioral and Experimental Agri-environmental Research, USDA Center of Excellence. And his research interests include the behavioral response to food risks and the interface between agriculture and the environment. He also has a PhD from Cornell University. When I discussed with Kent's participation in this panel, he said, well, I'm not a modeler, but Kent, I think one of the key questions is how we can better understand behavior. And then the challenge to the modelers is how to work with people like yourself to bring more of the behavioral elements into these kinds of analyses. So I hope you'll help us out with that. Let's see, and I'm not sure if, let's see, Pierre, you might need to release the screen. Yeah, there we go, sorry.
Good.
No,
I think we're okay here.
Kent's got control. Okay, great.
All right, hopefully you can see what I'm showing.
Yes.
Perfect. Well, thanks. John, can I just ask, I know we're sensitive on time and a little bit over from the 12:30 perspective. I'm happy to keep it short and sweet, but you can tell me how short and sweet I need to keep it.
If you can do 10 minutes, that would be great. I hate to make
That's fine. That's fine. I
mean,
mean,
less than that.
what I'll try to do is
what you have to say.
Yeah, well, thanks, John. I appreciate everyone being here and staying with it. I know that there was some technical challenges early on, and And yet there's been a lot of great information shared. So I'll try to keep it short and sweet, and perhaps be provocative to think about what what we're concerned about from the behavioral side of things, and give you a sense of where that's at. I mean, I think there's been a lot of discussion about these conservation programs that are in the United States, and it was nice to follow up on Pierre to talk about the behavioral challenges, because that's what I'm going to be talking about. But if we look at the the billions of dollars that are spent on conservation in the United States, and these are kind of what is underlying the idea of climate smart ag. I know there's a conversation on it. Is it profitable? The usually idea is, well, probably not without some type of subsidy, right? You're going to have to make some type of effort to improve the economic situation of farmers to really make it all worthwhile. And so that's why we spend these billions of dollars, or in part why we spend them. But they come in lots of different programs, from the stewardship program to the conservation reserve program to EQIP, and this is the federal level, and there's state level programs on cover crops like Spiro was talking about, and new efforts that are being pushed out. But we're talking in the billions of dollars. And the question is, how do farmers interact with these? These are voluntary programs in which no one has to participate at all. And in fact, most farmers don't participate, right? The majority would not be doing it. And so we think about, well, why? And that's a key question. Well, maybe we're not offering enough money, right? Maybe we're not offering enough money. Maybe it's just they don't really want to do these things. These programs are pretty cumbersome in terms of enrolling, and so there's a lot of transaction costs that muddle it down. So more than just the dollars and cents, and we'll get into this. And of course, in the last couple of decades, economists have really been saying, well, we can think about the perfectly rational expected utility maximizer, perhaps in this case a profit maximizer. But we know there's a lot of other elements that go into it, and these factors can be, relatively large and pretty meaningful in many different situations. And so by incorporating psychology and social and behavioral sciences, we're trying to get a better understanding of what makes someone sign up for these programs. And I'm going to say there's an element that I haven't heard discussed, but is ultimately key for all this modeling, which is the persistence of these behaviors, right? Just because someone does tries out a practice and adopts it now, does that mean they're going to keep it going? Because if we're talking about sustainability from a climate perspective, that's what we really care about, right? Is that persisted level of activity. And our research is showing really clearly that things like cover crops, actually a number of farmers do adopt them at various points, but the persistence is really a question. And you have to think about, what is persistence? Is it a question of every year they're using a cover crop, year after year after year? Maybe that's important for soil health and mitigating greenhouse gases, but that's rarely found in areas that have high cover crop adoption, either in the mid-Atlantic where I live, or in the Midwest where it's not as used at all. But it seems that there's obviously issues around planting and the weather that's there, and there's a lot of crop choices too, that your crop rotation seems to have a big impact. So these are things we're going to have to look at, both the adoption and the persistence. And unfortunately, there is not a lot of research out there that does it. And so that's kind of why we've got CBEAR going. And we were funded by the Economic Research Service to set up, to really embed lots of different research within USDA and look at key elements of behavioral insights, right? This kind of combination of economics and psychology and other social sciences. How do we do this? And to really come up with strong evidence behind it. And so that's what our group that is working on. I co-direct this with Paul Ferraro down at Johns Hopkins. And we go forward and we try to talk about these various behavioral insights. These are the kind of nudges that you hear a lot about, whether it's on how to eat less food, or better retirement savings, a lot of different types of things that Thaler and Sunstein have made famous, and applying them in the context of agriculture and the agri-environmental world. And so we put out a variety of insights there, and we work with USDA to help field staff think about this anywhere to like, how do you use behavioral science to sell conservation at the local level? How do you get farmers to adopt more of them? Let me highlight kind of 3 big areas that I want you all to be thinking about, right? And that about both the adoption and the impact persistence as well. We're going to look at time preferences, risk preferences, and then I'm going to have a kind of overall behavioral insights that we know exist out there. The key thing is when someone's thinking about a climate smart ag, right? Who are doing some type of conservation practice, I'm thinking about an intertemporal economic decision under uncertainty, right? Because there's going to be some short-term costs of adopting a new practice, right? I'm going to have to learn about it. I'm going to have to maybe get some new equipment going. And hopefully these things have, long-term benefits. And maybe that's to my, the globe, or sometimes a lot of these things are sold to farmers, frankly, under the soil health concept, right? That this is going to be something that is going to help them in the long term. You do cover crops all the time, you're going to have better yields there. But it's not like it happens right away. Even if it works in an ideal situation, it's going to be into the future, or the benefits to your local stream, even so you're fishing or your local environment, they're not immediate, right? These things take a while to have an impact, but those costs, they're going to happen right away. And so as soon as an economist sees a situation like this, where costs occur with certainty almost in the short run, and the benefits are uncertain, and in the long run, well, that's going to be difficult, right? We're going to be looking at the discounting future rate of benefits, and we need to think about that. And there's been very little work done on what farmers' discounted future benefits are, right? I mean, do we assume they're perfect profit maximizers and they just see it as a business decision, or are they putting in subjective rates? And that can be quite high if you look at the whole the hyperbolic discounting world. And we're doing research on this very topic with farmers to try to understand what those discounts rate, because that's going to be generally depressing. Like, this whole idea is it's going to mean that farmers are going to be adopting things less often than they might believe it would be the case, right? So you're going to have higher incentives, but keep in mind, sometimes these costs are immediate and the incentives are even paid out over time, right? So you have this other problem that, we often don't pay, the structure of these programs don't pay right away the full benefits to offset it. They've got, a discounting there. So these time preferences of farmers, a critical area that is necessary. And again, very little work done, especially in developing countries, right? There's been more work done in sometimes of international contexts where it's maybe easier to engage with producers than having large scale studies of farmers in the United States. The other idea is risk preferences, right? So will this actually, what are the other risks that I'm bringing on to my farm by choosing something? If I'm doing a cover crop, am I prepping my field correctly for a really good harvest the next year? What are the downside risks of choosing something, taking stuff out of production, putting it into a government program, right? Well, that may be fine if the price is right, but if we have a sudden spike in price, well, then the farmers missed an opportunity to make more money. That's that's a risk preferences. So that's going to be there. And so again, knowing about how to understand risks of producers is going to shape their cover crop decisions, right? Cover crops or other types of climate smart ag. And we generally find that these are both, we see that there's both risk averse and risk seeking in farmers, and that's actually true with people too, right? Where some people go out and are very risk averse in their insurance purchases, and then they'll go buy lottery tickets or do other activities that are pretty risk seeking. So we need to understand what is happening when they're thinking about conservation, and how are they going to be thinking about these gains and losses that could be out there. And we need to keep in mind that there's, of course, objective risks, which we say, the agronomists say, well, there's no idea that this is going to hurt your practices, but then there's a subjective risks too, right? That people just feel like, well, this is encouraging weeds, and these weeds are going to cost me more out into the future. And so there's sometimes subjective risks that certainly play into decisions for farmers on their adoption and persistence of cover crops. And again, I think this persistence area is a big one, right? We don't know enough about disadoption. of environmental practices, whether that's at the producer level or a lot of other practices where we just assume that once they're adopted, they're permanently adopted, not necessarily there. And for the sake of time, I'll just hit these other behavioral insights. But farmers are in communities, and they're making decisions that are observed often by their neighbors and peers. If they're doing a cover crop, that's observable by their neighbors and peers. And so how that impacts their social norms and peer effects is important. You often find the discussion that older farmers are less likely to want to have weeds in their fields, and that will be something that a younger generation is more comfortable with. And so how do you understand those social networks? How does that pass along and move forward? It's not just an education. There's about what's my standing in my community, and also how do I have a personal identity, right? But to what degree do I think of myself as an important environmental steward and taking good efforts, not just to produce food for the world, but to be a steward of my land? Those type of identities run strong in the conservation community and the farming community in the United States. And so understanding those things and how do you build them forward. You see a lot of state level programs that put signs out on the road saying, hey, this is a climate smart or a water smart farm or something like that. Those identities are important. The complexity is something that we need to look more at, but these things are, we cannot assume that there's no transaction costs. And the number, I don't know if it's the number one thing that farmers complain about, or it's just a consistent problem, is these programs being run by the federal government tend to be difficult, like filing taxes or filing the FAFSA form or other things that are government oriented that tend to be high concerns about everyone checking every box correctly and making it quite difficult as a barrier, especially if you're not a person who loves government forms, right? And so these are transaction costs, complexities there. And finally, anchoring and defaults is something I want to highlight. A lot of these we often find that people are driven by the defaults. And so if the default is not to do conservation programs, then that continues and it moves forward. Or in the case of the Conservation Reserve Program, when farmers sign up, the general default is they choose the least environmentally friendly behavior. They choose a seed mix, which is kind of mild, but they're not choosing the pollinator friendly, climate smart friendly seed mix. It might be a little bit more expensive, but they could be choosing these other practices. But USDA tends to set the default at the lowest level to get it started. Well, maybe we should start at the highest, saying, hey, here's what you should be doing, and maybe you don't do the full best seed mix, but you take the second step down or not. We know that in lots of contexts, how a choice architecture is framed or how a default is framed can make a big difference on impacts. Now, I don't know how exactly you're going to incorporate all these issues, and that's maybe why I told John I'm not a modeler, so I can just throw out lots and lots of problems here. But these are things that we are actively working on. The literature is still sparse in this, especially in the United States. But I think they're important questions, and I think Pierre hit that early on, right? Talking about this is going to be something that is going to be impacting your models, and most of these cases are going to be leading you to less adoption of conservation than you might think of if you use a traditional economic model of just saying, hey, this should be working out well. Maybe someday we'll get the social norm changed and everyone will be doing some type of practice, but that's not where we're starting at from today. So I'll stop there. Again, thanks for your time and attention. And if there's questions, I'll answer them in the chat and so forth.
Great, thanks, Kent. That was very excellent presentation, and I think a really nice balance to what we heard before. I see Terry is about ready to introduce our next session. I guess we've overstayed our welcome here a little bit, so I'm just going to wrap up.
I would love to have more time, and so many critical issues have been put on the table, both in terms of economics, profitability, and these interesting challenges of adoption. But we do need to forge ahead, and look forward to
well, Terry, let me just finish with one final comment. Okay, if you'll give me 5 more seconds.
Of course.
I'll just conclude by our panel by saying that, you know, some of these issues that Kent raised, you know, I think it really will be nice to see some progress in that area, so that the people doing the behavioral models can begin to have some notion of, you know, the magnitude of some of those effects that Kent was talking about. For example, in my own work, we use threshold adoption models, and if we have some idea of the magnitude of some of those transaction costs and other behavioral effects, time preference, risk preferences, we can start to incorporate those into our adoption models. So maybe that's just one way to kind of tie that all together, and just say thanks to all of our panelists and to Spiro for an excellent session. Yeah, and apologies to the next crew for running late and our little technical glitches along the way. But anyway, and just finally, yeah, hope all of our panelists can take a look at the Q&A and respond to some of the questions, at least online. Thanks, Terry.
Thank you, and thanks to everyone that's been part of these great discussions. Our next session is on COMET,